Graham is an old friend, and I'm very, very glad that he agreed to give a presentation. Dr. Graham is the Program and Project Coordinator of the International Data Center Division at the Comprehensive Nuclear Test Ban Treaty Organization in Vienna. He holds a PhD in geophysics from the University of Edinburgh. He's been with the CTBT since 2015, but in fact, Dr. Graham has been involved with the CTBT going back to the early 90s when he was the National Data Center Manager in South Africa. And a true expert on all things seismic and all things nuclear testing, including coordinating the organization's response to the DPRK's test in the most recent test in 2016 and 17. So, Gerhard, I will give it over to you. Looking forward to your presentation.
Good morning, John over there, and very good to see you. And also good morning to all the participants. I'm really glad to be here, and I'm looking forward to this interaction. And I need to find my presentation and share it. And I must say that currently we're not using Zoom. So it may be a first experience for me now, but let me see. If I have any problems, I'll shout for help. No, I think I first need to share my screen at this stage. So let me do that. So, John, can you just confirm that you can see the slides? Okay, that's good, and everyone can hear me. So I'm going to focus a little bit on the technical side of things. John, I enjoyed just hearing you talk about the negotiations and I think some of the activities that happened those years, and sometimes we forget a little bit about it. But it is really a very holistic picture, I think, that that one must work on, and important to remember where it all started. So I'm going to start off with taking a look at the verification regime, which consists of what we call 3 technical pillars. This is what we have in place, and currently in the structure of the organization, these exist as divisions, each with its own staff and its own functions and responsibilities. So the international monitoring system refers to the network, but back here in Vienna, it's also a division that is responsible for the gradual build-up of the stations, the number of stations. We've reached about, well, just over 90% that have been installed at this point. Then there's the International Data Center. This is where I'm based in this division. And the IDC is responsible for the operation of the IMS. So very close link between these divisions. And then, of course, there's the on-site inspection. But the on-site inspection, the division exists, but currently in a sort of build-up environment. The on-site inspection group is gradually developing their procedures, all their documentation. As one can imagine, this is a very sensitive aspect of the treaty. This is probably the most invasive part of the organization, and this will only really come to its full potential after entry into force. And you will also see that I'm not going to have too many slides on the on-site inspection, but I will briefly touch on that. So there are, in terms of the compliance to the treaty, there are 4 elements of the CTBT verification regime. I mentioned the IMS, so there are 337 facilities. I'll tell you a little bit more about that just now. There's the on-site inspection that I now already mentioned, but there's also consultation and clarification. In other words, in the treaty, all member states have the right to clarify matters, whether it is indicating a possible non-compliance by another member state, or vice versa. A member state also has the right, of course, to show that that it is complying, and that whatever claims is made against it, that there's a logical explanation for that. There's the confidence building measures, and we referred here to large chemical explosions. Those are obvious environments that I remember in the early years. I was involved in the national network back in South Africa, and this is one of the things we had to do already early on after South Africa entered and signing the treaty. With the many coal mines, it was important that this information is given through to the Provisional Technical Secretariat, the PTS, so that there's no misunderstanding, no interpretation that can lead to some misunderstanding in terms of these large explosions. And the same is true for many parts of the world. And often nowadays we also see that with the infrasound data that we analyze, a lot of that comes from areas where we know there's mining happening, and there's open cast mines of large explosions. So I think many of you may have seen this map before. This is the build-up at the point when it will be completed of the International Monitoring System network. In total, 337 facilities. It's made up of 321 stations and 16 laboratories. And here, a little bit more in numbers. So there are 170 seismic stations. So let me just for a moment dwell on this. And I have quite a few slides, but I'm not going to go into detail on each and every slide. Some of it I will just very briefly say a word or two on. But I think here it's important that for your understanding, the seismic, so there are 4 technologies of the IMS. Seismic being the technology, if we go back to the treaty and we read that this is a complete ban on nuclear testing anywhere by anyone, then that anywhere includes underground and the surface. It includes in the oceans or underwater, and it includes the atmosphere. And these technologies were specifically designed to safeguard those areas, to monitor those areas, to verify that no one is either doing tests in any of these environments themselves, no country, or that no one is allowing any other country to use its territories for this type of testing. So seismic specifically is aimed at underground and also surface events. And when I say events, I imply anything that could be a man-made explosion, or a natural earthquake. The explosion may be of nuclear or non-nuclear origin. So seismic is really the technology that will give us the first indication that something has happened. There are two types of seismic stations in this technology. We refer to these as the either the auxiliary stations or the primary seismic stations. So the primary seismic stations physically belong to the treaty, belong to the and are looked after by the PTS in terms of maintenance. There's 50 of them. The other 120 are auxiliary seismic stations, and these are stations that were sort of committed during the negotiations by many different countries, and as such the PTS has no direct responsibility for the upkeep and the maintenance of the auxiliary seismic stations. Then hydroacoustic, there are 11 of these stations across the globe. And the reason that we can get away with only a few, it's also a good thing, is because, of course, hydroacoustic stations are very, very expensive to install, as one can imagine, in the environment of the ocean. But because we have particular channels in the ocean that allow an easy propagation of sound waves. Waves can travel around the oceans for a very long time without much attenuation, and hence 11 stations are quite sufficient at this stage. Then there's 60 infrasound stations. So these are stations that in particular monitor the surface, also including the surface and the atmosphere, of course. And radionuclide, there are 80. Particulate radionuclide stations, I'll tell you in a while a little bit more about the difference between particulate radionuclide stations and noble gas radionuclide stations. So here you see the buildup of the IMS network. So over the years, going way back to the late 1990s, 1999, it started, and it's the 4 technologies. But here we've now split the seismic into its primary and auxiliary components: infrasound, hydroacoustic, radionuclide, and it includes the radionuclide laboratories. At complete level, there will be 16. Currently, there's 14. So you can go through the table on the top left and see the current status. So we refer to certified here. That's maybe a word I should very briefly explain. A certified station means the station has been installed by the IMS division. It's been tested. In other words, the station has gone through a set procedure to show that the station adheres to the requirements of the treaty, that it adheres to the technical requirements, that it can send signed data, and that data can be communicated at the right level of data availability to Vienna, to the IDC, and here that data will then, once the station is certified, it will enter the operational environment. We refer to it as the station enters ops, or operations, in the IDC. That data becomes available to our member states, and it is also used for the production of the IDC products. So there are stations that are at different stages. There are stations that have been installed, but they have not yet been certified. And if my memory serves me right at this stage, there should be about 11 of those stations. They're working, but they're not yet in operations. In fact, we received that data in a test environment. And then, of course, there are stations that is currently being built. They're in construction, and there should be about 6 of those. And then there are those stations where we're still at the level of negotiations with some countries. But if we add all of this up, we'll see that the IMS is currently at about 93% complete. So this very colorful picture, let me just really say, this is the first thing that you will notice is it covers essentially the entire globe. This is the footprint of the global communication infrastructure that we use. It consists of 9 satellites, and these satellites are responsible for picking up the data from the stations, and through different routes transmit that data to 3 different surface stations, and from there the data arrives here in Vienna at the IDC. There's a lot more, I must admit, behind all of this, but I think for what we need to know, that there's a particular infrastructure in place that makes use of mostly satellite communication, but also we have seen in the development of the GCI, we now at the 3rd generation already, and each generation lasts for 10 years. That is a contractual situation or a contractual limitation. We are also moving more and more to internet, to landline communication. It's become very stable over the last 20 odd years. And this is how the data is communicated. By the way, the data availability requirements for any link that is used within this infrastructure is 99.5%. That is what is required in terms of getting the data securely. There's also encryption that's being used, but that's to ensure data gets to Vienna quite securely and quickly. So this is a very sort of a mosaic picture of behind this data transmission. You see the new CTBTO operations center. This is like a window into the data arriving, the state of health of the stations, the state of health of the communication interfaces, and the production, the different stages that we go through in producing automatic products and also reviewed products. And again, on each of these little windows that you see here, there's a bit of an explanation behind it, but I think all that is perhaps required here today is that you're aware that there's an operations center. It's manned by operations officials, staff that as a rule, or as their routine every day, just monitor the data and the data quality and any potential problems with any of the stations or communication links that we use, and deal with it immediately through incident response, alert systems, and we can resolve all matters fairly quickly from here. Those matters that do not require, of course, maintenance engineers to go out to the field, to the stations. And what I should mention is that the PTS, while it is in its provisional operation phase, because as you have now heard, we are not, the treaty has not become legal yet. We've not reached entry into force. We work normal office hours, or we like to say we work normal office hours, but it just means this op center is not manned 24 hours a day, 7 days a week. And John, you can prompt me at any point if you want me to hurry along a little bit, but I thought the IDC pipeline, it looks far more complicated than what it really is, but a few words on that. So this is a schematic view of how we receive our data from the 4 technologies out in the field, and what do we produce? What do we do with this data? So the first and probably the core of it all is the seismic data. And the seismic data arrives first. Usually, as I've said, it's the first indication we get of any event worldwide. And one of the reasons is that, for instance, primary waves, so-called P waves from an earthquake, for instance, propagate at in the order of 6 to 6.5, even higher, 1,000 meters per second. So it gets to the station very quickly in comparison to, for instance, wave speeds in the oceans or in the atmosphere. So we tend to get that data and process it all within an hour from across the network, from the primary seismic. So those 50 stations, and we currently are at 44, they form the core of building any event that occurs. At that point, we then send a request out to the auxiliary stations. And it's an algorithm that looks at how large was the event, or the initial indications at least, and where did this event occur, and that makes a decision in terms of which auxiliary stations to then basically call on to provide data for further analysis. Hydroacoustic data will arrive, and the first product is known as the Standard Event List 1. That is released after an hour. It's an automatic product. After 4 hours, so in other words, 1 hour plus 3 hours later, we now have auxiliary data, we have hydroacoustic data, we have seismic data. So it's an enhanced analysis. It's still automatic, and the Standard Event List 2 is released. After infrasound data, that will now, it's the latest or the last bunch of data that will arrive, and this is mostly because the infrasound data, it takes much longer to arrive at the stations, and it's much lower frequency data, it's much longer and larger files to transmit. So the infrasound data will arrive, and it will be in time, some of it for Standard Event List 2, some of it for Standard Event List 3, which is the last automatic product. It's produced after 6 hours. So typically then within 6 hours of an event, we will have our so-called cell 3. That's the final automatic product. After that, we will now have our analysts that will review the results. They physically go through all the data. They will read time events, they will add stations, they may reject stations. And I have to apologize, my phone is ringing here on the side. And I think if we may have a couple of those interruptions. So once the analysts have reviewed it, we release the reviewed event bulletin. That's in a way, the final product in terms of a complete list of all events for any data day. There's a screening process that happens, and this is where, through applying some algorithms, it's an automatic process that will lead to the so-called standard screened event bulletin. And this is the bulletin that will take out all the natural events, I should say events that are clearly natural, but those events that may require a second look or further analysis will remain in the standard screen event bulletin. And this is particular to the benefit of our member states, so that they can use this bulletin to look further into any events that they may have some concern about. Radionuclide, quite different. In this instance, we are analyzing filters or noble gas, extract of a noble gas from air samples, air that we suck through for the particulate. We suck air at a high rate through filters. For the radio xenon, we suck air over or essentially charcoal, activated charcoal, and we cipher out the only a few milliliters of the radio xenon. And essentially it goes through a very similar process. There's the automatic product that is produced, the so-called ARR, the automatic radionuclide report. In the case of the particulate stations, it takes about 3 days because we're dealing here with isotopes. And isotopes require time to rest because we are only interested in particular isotopes. We refer to those as the CTBT relevant isotopes. And for particulate, there's more than 80 of those. So the data collection takes about a day. This is the time of sucking air through filters. Then there's another 24 hours during which the filter is allowed to rest. And this is for short-lived isotopes to decay. And then there's another 24 hours required during which these filters are now placed in a detector and counting happens. So this is the process through which we establish which isotopes are present in the sample. And then that initial spectrum is then communicated to the IDC, and the first spectrum that is released and categorized is automatic, and then it gets reviewed by the analysts, and the reviewed radionuclide report is released. The same happens for noble gas, except here we're only interested in 4 isotopes, xenon isotopes. The product that refers to the fused event bulletin, that is not produced yet within the IDC. We have tools available that will allow member states to produce their own fused bulletins, but it's not yet done within the IDC, and there's maybe still a discussion on whether the fused event bulletin will become an IDC product. Very briefly on this, here you get a glimpse of the number of events that the IDC has dealt with in the last about 20 years. More than 600,000 events. So that gives us what, about 30,000, I think, in a year, on average over 20 years. And most of those, of course, are earthquakes, with a few special events in between. And we'll talk about some of those later on, mostly the DPRK announced tests. So here I'm going to fairly rapidly go through the capability of the network. As one can imagine, as the network is being expanded, as it's being built up, the capability agrees and improves. And what we're looking for here on the seismic side is the ability of the seismic technology of the network to detect smaller and smaller earthquakes. And I will flick between the 2 maps. You can see the brighter colors in the second map. This is the move from 2006 to 2018. And these brighter colors shows us that we are moving the spectrum towards smaller events, which is good, because once we get to magnitude 3.2, and yield is also, it's a very difficult parameter to really discuss succinctly, because there's so many unknowns. But once we talk about 1 kiloton explosion, we're in the order of about magnitude, let's say about 3.5 to 4. And hence, that's really what we're aiming for, because this is what the network is designed for, is to detect 1 kiloton of explosion in terms of yield. And the same can be done with all the other technologies in the network. Here we're looking at hydroacoustic. Again, the bright colors shows us that with 11 stations, how extensively we can monitor the oceans. The blue colors, the darker colors, are areas where either the stations are blocked or where through whatever reasons there will be some difficulty with propagation of sound waves in those parts of the oceans. It's a very, very capable component or technology of the IMS, and I hope I get to the slides on what happened at the time of the analysis of the unfortunate loss of the Ara San Juan submarine. Same is done for infrasound, and here again we can see the move over some time from 2016 to 2017 in the infrasound component of the network. And here we see something similar for radionuclide. So this is the capability of the radionuclide network as a whole. And again, what we want to see are the bright colors, the reddish colors. And we can see moving from on the left to 2006 to 2017. This is specifically linked to the period of the DPRK announced tests. We can see how more and more stations were added and improved the capability for different isotopes of the radionuclide laboratory. And this is just about my only slide on on-site inspection. So this is a final verification measure. If through the detection of any event, there's a concern about the origin, the nature of a particular event. And all measures in terms of clarification and further analysis have been used and exploited to the full. And if there's a final authorization through the Executive Council, then an on-site inspection can be done. Not at this stage, not while we're in provisional operation, but after entry into force. There was one big field, integrated field experiment. This happened in 2014 in Jordan. I think there's a video that is available that one can follow to see exactly how this was done. It's very interesting, but it's an exercise that's fairly complex and very, very involved to plan and develop and execute. So in terms of ATM, this is in particular, so ATM is the atmospheric transportation models that we use. This is needed for the radionuclide side of the IMS. And this is essentially to allow us two things. The one being that if we do have a release from anywhere in the globe, whatever the source is, we can use the ATM, the wind patterns, the wind direction and wind speeds, precipitation, to predict where would this release in the form of a plume, where would it move to? Which stations should we be monitoring for potential detections? But we can also use measurements at stations and do a backward simulation to see where did this plume come from, the measurement that we made, where is the origin, and we can do that, and I have a few of those to show you as well. And now I'm getting to the detection of the 6 announced tests done by the Democratic People's Republic of Korea. The first goes back to 2006, and the objectives in terms of the verification regime were always the same. This is that we need to be able to collect this data, we need to be able to process this data, we need to be able to make the results available to our member states, to our state signatories, that we need to make this data available in near real time, that the products are produced within the guidelines of when there's a test like this, we do not follow provisional operation guidelines, but we follow after entry into force guidelines. Of course, what we're also looking for is accurate location, in other words, accurate results, and to assist our member states to form their own opinion, to form a final decision. This organization is not there to categorize events. We do not make a final decision or a final release or announcement on whether an event was an explosion or not, whether it was a nuclear explosion or not. But we provide the data and we provide the tools to our member states so that they can do it, so that in combination with IDC results, IDC products, and national means, national capability, a final decision can be made. And I think what is also important here, I want to quickly quote a couple of things, is that in comparison from 2006 to 2017, of course, there was a massive growth in the network. The time in which, if we look at 2006, the final automatic product was produced after 12 hours. In 2017, it was produced within 6 hours. When we do the screening, we apply the screening criteria, that the event is not screened out. In other words, that when, in this case, there's an announced test, and we have the final results, and we put those results through our screening criteria, that our criteria are sufficiently developed to recognize this as a non-natural event, because that creates the standard screen event bulletin, and that is what is used by the member states. So very briefly on this picture, so at the time in 2006, we had access to the test, the seismograms recorded at the stations, but we also had some natural events from about the same area in the DPRK. And when we compare those, we get a striking dissimilarity. And this can be quite well explained through the theory of the source process behind all of this, explosion versus a natural earthquake. But what we see on the left is the 9 October 2006 announced test versus an earthquake in 2002. And we can see the impulsive, strong arrival from the explosion, where on the right, it's a more gradual arrival. But we see later on, there's a lot more energy that comes through as surface waves. And these are what I'm showing here in sort of graphics as seismograms, is essentially what is also built into the screening criteria that is being used. We look at the amounts of energy in different frequency bands for different types of arrivals. We're looking at how much energy in particular is present in the so-called surface waves. We compare the amplitudes of the first arrivals, the first 4 seconds or so, and we use those to automatically determine whether an event stays behind as a potential event of interest, a potential non-natural, or it gets screened out as completely natural. So here I want to show you a very first example of ATM that was used, and this is to show you how we would then, through forward modeling, start identifying potential stations. Here we see the plume reaching CAX16, for instance, and CAX5 in Canada. So this allows the analyst to pay particular attention to the spectra, excuse me, from these stations. And in this instance, in 2006, and I will move on to the next slide. And what I want to show you here is at the bottom, we see this sort of orangey curve, and that's a prediction that came from the forward simulation, where we said, if we consider a release at the time of the test on the 9th of October 2006 in North Korea, then we would expect, if it reaches this particular station, CAX16, we would expect a peak in this xenon 133 signal at CAX16 at this time, this date. The gray bars at the bottom indicates other sources in the area that could potentially influence what we measure. But if we look at the blue graphics, the top curve, then we see, as predicted, we did see, and we did make particular measurements, strong measurements for xenon 133. And this is the first announced test, and lo and behold, not only did we get the location very well with the seismology or seismological stations, but we could also, through the measurement of isotopes and use of ATM modeling, could also show that the release from this particular test did reach at least one of the stations in the radionuclide stations in the IMS. This was in 2009. Now you can see there's a lot more stations. I've included here both primary and auxiliary. 2009 did not, the release was not recorded at any of the radionuclide stations. I'm going to skip over that, although there were a few radionuclide stations in the area already. We could not positively identify any release. So when I say a release, then what I'm implying is either at the time of the test, there could be leakage, and we may even see particulate isotopes like cesium, iodine, and so on, reaching the radionuclide stations. Or there could be, over some time, radioxenon can actually find its way through the rock mass and can get to the surface. You don't need to open the passage or the tunnels to release the gases. Radioxenon it's very permeable. It can diffuse fairly quickly. What we have seen in two occasions was exactly this, was the release of radioxenon, and this is the only way. So the technology such as seismology, hydroacoustic, and infra it can tell us there was an event, but it cannot tell us whether this event was nuclear or not. Radionuclide measurements is the only technology that we have that can identify whether this was just a chemical explosion or an actual nuclear explosion, because we're looking at fission products in this instance. So this was in 2013. We can see the growth of the network. In 2013, I can already, while you watch this plume moving across Japan, in particular one station, Takasaki, and you'll see this plume will also reach a station in Russia, the Russian Federation, RUP 60. So In this instance, we could also link a release at the time or just after the test was done. But we did it a little bit differently. This was done through the fact that we recorded two different radio xenon isotopes, 131, the metastable, and 133 at the station in Japan at Takasaki. So the modeling that we use here can assume one of two scenarios. Either we say that at the time of the test, there was a release. So we call this a puff. It's a puff release, and we usually take it for about 3 hours. But what we more often do in our modeling is to assume a continuous release. And this is why you'll see that this plume keeps going, because we know that the nuclear material, it's not a big bang and then it's gone. No, that material is left behind in the cavity. It stays hot, and it keeps on releasing radioactive material for a very long time. So in essence, the release can happen over a long time. So we normally will consider up to 3-4 months after a test, at least in the instances that we had the tests in the DPRK. So here we had the Takasaki 2 instances. We looked at xenon 133, and we saw, because it's important also to understand the history at the station, because there's many other sources of radio xenon. It's not just a nuclear test. It's released through nuclear power plants. It's released through medical isotope producers. There's many different releases that we do see across the globe, and in particular in Japan at Takasaki. So here from 133, we could not really see anything that immediately stood out. But when we looked at, and I'm sorry, when we looked at the 131 metastable isotope, we can clearly see at least 2 measurements that are way above the usual detections at Takasaki. So that when we did, oh, I'm sorry, I thought I had the ratio calculation in here, but I did not. So when you look at the ratio between 131 and 133, this is exactly what we got. We could clearly link that to the time of the release of DPRK in 2013. So in 2016, we had 2 tests, one in January and one in September. And none of those we could positively link any radioactive release. But what again we saw was quite a remarkable improvement in our uncertainty. And here is the really big test that was done in announced test on the 3rd of September 2017. It resulted in a really extensive response from the IMS. You can see primary stations, auxiliary stations, hydroacoustic stations, and even an infrasound station. A nearby infrasound station recorded the reverberations in the air from the ground that was really violently moved at the time of this test. In fact, maybe let me just take a step back, and this is the comparison. And I want to point out 2 or maybe 3 columns here. The one being the magnitude, the body wave magnitude. We can see the increase here from 4.08 in 2006 to the test in 2017, which was a 6.07 or 6.1. Keep in mind that for every increase, it's a log, magnitude is a logarithmic scale, so every increase of 1 signifies a ground movement of 10 times larger and an energy release of about 30 times more. So if we move from, for instance, magnitude 4 to 5, it implies 30 times more energy and 10 times larger ground movement. If we move from 4 to 6, it implies 900 times more energy and ground movement of 100 times larger. Many more stations, as we would expect. I mean, you saw the curve, the IMS was expanded all the time. But look at the at our uncertainty, and you can look at the last figure, the square kilometer. This is a confidence area, which is an error ellipse. In 2006, it was 880 square kilometers. In 2016, it reduced to 109 square kilometers. This is very important for OSI because it means that in the OSI regime, the largest area they can investigate, there's a limit on it, it's 1,000 square kilometers. So in 2006 already, the IMS results gave us something that was within 1,000 square kilometers, but 1,000 square kilometers is a very large area to investigate if you don't quite know where to start for an inspection team, or I should say the inspection team. But 109 square kilometers is a lot more doable. In fact, you can pick a larger area and gradually work in, but it says, and it helps a lot more if ever an on-site inspection would be required. So in the graphics form here is what happened from 2006 to 2017. And you see those nuclear signs. And that's to indicate that in 2006, we made a detection at the radionuclide station, and also for the very first, or for the test in 2013, not for the free in 2017. That's how it looks in graphical format. If we compare the seismograms from 4.1 down to essentially 6.1, that is not allowing the equipment to adjust the signals to all look the same. This is essentially what one would expect the real ground motion to reflect from 4.1 to 6.1. And as I said, it merely is a reflection of 100 times larger ground motion. And again, in graphical format, so if we look at the green elliptical area, then that is the 880 square kilometer zone. It's the 90% confidence interval. If we compare that to the red, which is 2017, and that is the 109 square kilometer zone, it gives you just a real sort of aerial view of what an inspection team would have been up against if there was, let's say, an inspection in 2006. So something else that is in the treaty, excuse me, is that the treaty has particular paragraphs about doing further analysis to help assist member states to find the source of the event. There are two ways we can do this. One is that we reanalyze the data from the IMS. This is known as special studies. Or we can do an expert technical analysis where we can use other methods and include other data as well. And this is what was done here as an overview slide with the 6 announced tests. This is using relative location, cross-correlation between waveforms. And if one would compare this with the calculated origins, we see a slight shift in the picture. For instance, the 2006 location has moved more to the east. But what is also interesting is, if you look at this green ellipse, is the location of the last announced test, the September 2017 test. And it's not a dot, it's a zone purely because it was so large. And when it's so large, it means it's a fairly large area that was displaced. And it created nearly like a large earthquake. It's a much more complicated, complex waveform that we have to deal with. There was, of course, also an aftershock. About 8 minutes after the main blast, there was an aftershock. This shows the level of disturbance in the natural stress field. And this is an indication. I think what you need to compare here is the red dot in the middle, which is just a graphical way of relatively show the position of the main shock, the explosion, and then that dark blue area essentially at about or sort of to the northwest, and that indicates the zone in which the aftershock took place. And then if we, from there on, if we, after the analysis of all the aftershocks at the time, if we plot all of these, then we see this sort of active zone that developed after the main explosion or the test, which is shown by the red dot with the small red ellipse. And then, of course, the aftershocks have these large ellipses because the result is not so well constrained because there's not many stations that recorded the aftershock. This was the picture at the time of the radionuclide stations in the area. And I, again, just want to briefly show that it's not, when I say we could not positively identify any measurements at radionuclide stations that could be linked to the test. In essence, we had some measurements. This is measurements that from 2 stations in particular, Takasaki and at the station in Hawaii. But when we then now compare the possible source zones, source regions, and we overlay them, then, and I will just draw your attention to the figure at the bottom. You look at those orangey areas, you will see that, yes, one of the orangey areas is right on top of the test site in North Korea. But it's not the only possibility. There's another orange zone a bit more to the northeast, and hence, because we could not uniquely identify or link the measurements with a release at the test site, we cannot beyond any doubt say that yes, we did record something. In this instance, strong indication that yes, what we measured came from the test that was conducted, but we cannot say it beyond any real doubt.
So, may I ask if we could perhaps wrap up?
So I'm going to wrap up, John. I'm going to flick through some of the civil and scientific applications, and this is merely to say that while we are developing the verification regime and we are at the time of provisional operation, we also have to think along the lines of exercising our data. We need to apply our data and make our techniques better. And this is one way, is to use the IMS data in combination often with national data in typical civil problems that we may experience, scientific applications, research that's being done, because the benefits that we get from that can one day be applied for verification purposes. We see, for instance, what happened at the time with the Fukushima accident. And unfortunately, I've got a lot of slides. We all know that Fukushima resulted. I want to show you this. Keep an eye on the map of the world, and you see how with time after this accident, the station started essentially lighting up in red, and red meant level 5, multiple fusion products that were detected. It just shows how at the time in 2011, already with the development of the radionuclide network, how effective it was. I want to, and of course, data is being used for tsunami warnings in different parts of the world. But I want to skip over all of that, and I want to come to the case of the search for the Arasan submarine, where we know that at the end, this data came from only two of our hydroacoustic stations. We did an expert technical analysis. In other words, we incorporated data from a seismological station that's not part of the IMS. We were able to identify a particular zone in which we believe that the location of, or at least the last location of the submarine was in. And as it turned out, when the wreckage of the submarine was found, that this was well within and very close to our initial estimates and assessment. And I want, if you look at this, you think immediately, and I'm pointing out to those little red lines essentially that you see in this background of blue and yellow and green. And that's the signal that came from the submarine, whatever happened at the time, unfortunately. They're so clear, but it came from stations that were thousands of kilometers away in the ocean, with all the background noise that we have in the oceans. And we could still use these two stations to find a location. And I wish I had more time to tell you about capacity building and how we use this to ensure that all our member states get to a point where they can independently verify the results produced by the IDC. This is all done through capacity building. I'm going to leave you with this slide, because this is the heart of the capacity, the integrated capacity building in the organization, in terms of the different trainings, the workshops, software, and even equipment support that we provide to our member states. So John, I'm going to stop here. I think perhaps we can take it further with questions